Hello and welcome to this session where we are going to cover some of the theory of week 4 and look at some of the examples. So there are these three topics that we'll be looking at. So form theory we'll be presenting as an extension of what we did last week with the boundary conditions. And once we have this, then we'll go on to generalizing our balances. So far, we have been dealing with specific cases of the mass balance. So of course, we also want to cover the energy balance and the momentum balance. You've done the momentum balance in the first part of the course, but we want to show that all these balances fit into a general framework. We also want to, as part of the generalization, generalize the geometry. So it's not just about the nature of the variable, whether it's concentration, temperature, or velocity. In addition to that variable, we want to generalize the geometry. So far you've been seeing the slab geometry, the cylindrical geometry, the spherical geometry. So we want to look at a way to write the balance such that it is independent of geometry. And that sounds like a tall order, but we'll see there are some very elegant mathematics around that. Then we'll look at the numerical solutions. So numerical solutions are not really part of the course, but still it's useful to understand how we have a hope of ever solving these equations. So the equations we develop are going to look pretty difficult to solve, and so numerical solutions are always available to us. So you will encounter many techniques later on in the academic program. So at this stage, we just want to look at a high level, the types of results that we can start generating when we couple numerical methods with our generalized balances. So let's look into form theory first. So just bringing up the set of notes here. And I'm just going to stick pretty closely to this because this has some well-drawn, according to me, diagrams here. So in form theory, we are in essence trying to simplify our development. So we have already developed our material, the material balances in terms of boundary conditions. And let's just think about a simple situation. Let's think about a droplet of water. So here's our droplet. So you've got a droplet of water sitting on some surface. And then you've of course got air around that droplet. And now if you think about the water molecules in that droplet, so you've got a very high concentration of water in this droplet in comparison with the concentration of water in the gas that's around that droplet. So even though it's a gas, we know that some water molecules will escape into that gas. And we are interested in the concentration of water both in the gas and in this liquid. And it's not such a straightforward calculation, or it's a lot more complex when you zoom right into this. So let's zoom in here. So if we zoom in, so let's say this is a 2 millimeter droplet of water. And let's say we are now zooming in at the angstrom level, so 10 to the minus 10 meters. So if we zoom into this part here, then you can see we are looking at two phases. We are looking at a liquid and a gas. And we might well see a picture like this, right? A picture like this, let's say. So on the liquid side, we have a certain concentration of water, and on the gas side, we have a certain other concentration of water. And of course, we expect that on the gas side, the concentration will be lower than in the liquid. And there are a couple of things to notice. Number one, we expect that there will be an equilibrium shift between these two phases, right? So in the liquid, we of course have a high density, a much higher density than in the gas. So in the liquid, we know that the density of water is about 1,000 kilograms per cubic meter. And in the gas, it's on the order of between 1 and 2 and 3, depending on the pressure and so on. So your concentration is about 1,000 times less in the gas. In addition, there is no guarantee that we are at the saturation limit, right? So we can talk about the saturation limit of water in air. So just because the maximum amount of water that the air can carry, let's say, is 2. Let's say the saturation limit of water in air is 2. That the most air can carry is 2 moles or 2 kilograms per cubic meter, right? Now, that doesn't mean that the air that we have out here is at 2 kilograms per cubic meter, right? We might well have a dried body of air. For example, this droplet might just be sitting in an oven that's busy boiling it off, but before it's boiling off, the air is very dry in that oven. So just because the saturation limit of water, the maximum amount of water that can be carried in that gas, just because that might be some value, doesn't mean our gas in the bulk is at that value. So going back to our picture here, so we can talk about a bulk value of concentration. So out here in the bulk, far away from this droplet, there is some concentration of water. By the same token, we can talk about the bulk concentration of water in the droplet. So even though the droplet we think of as a small space, still far away from this interface, right? Far away from this place where we are zoomed in. It might be that the concentration here is much higher. And that might simply be because near the interface, water is being lost to the air, right? Of course, if this was a pure water droplet, then we wouldn't really say that. But if this is, say, some mixture of water and some other solvent, then you could say that, well, water is leaving the droplet and going into the air. And so near the surface of this droplet, the concentration of water is lower, and maybe the concentration of the solvent is higher, right? So you see, all these things are going on. As water leaves the liquid phase for the gas, it depletes the water that's left behind in the liquid here, and it increases the concentration in the gas here. So it leads to a picture like this. So if this is the interface, if to the right of this interface we have the liquid, then there will be some bulk value of the liquid. So Ca2b, the bulk value of component A in the second phase, right? So to the right of this interface is phase 2, and in phase 1 we also have some bulk value of the concentration of A. And so that bulk value of A might be much lower than the value that we see at the interface, because across the interface A is entering into this phase. Right, so because you have a certain bulk concentration, which is not necessarily the same as what we have at the interface, then there's going to be some possibly continuous shift from the one to the other. So we can imagine that between the gas and the liquid, there exists some equilibrium. Right, so as we said, it might be that there's 1,000 kilograms per cubic meter in the liquid. So, well, that's really in the bulk, and then there's 1 cubic meter, let's say 1 kilogram per cubic meter in the gas. And that might not be the same as the concentrations that we have at the interface. So because we are losing water to the gas, the concentration at the interface on the liquid side might be lower than in the bulk, and then by the same token, on the gas side, the concentration at the interface might be higher than the concentration in the bulk of the gas, right? And however close those values tend to become, there will still be some discontinuous shift between the two of them, right? Remember, up here on the liquid side, we are talking about densities on the order of thousands and hundreds. Down here we are talking about concentrations on the order of ones and tens, right? Not even tens, right? Probably between 1 and 5. So there is definitely going to be some major shift. So across this interface, right? And remember, an interface is not a real thing. It's if you like, it's a zero volume thickness. And so across this interface, at the point where we just become liquid, our concentration is much higher. At the point where we just become gas, the concentration is much lower. So there is going to be a discontinuous shift between the two phases. And we typically deal with that using an equilibrium constant. I'm just looking for in the notes. Yeah, it's up here. So we are saying where x equals 0 minus, right? So we are talking about x in this direction. So if we are looking in the x direction, which is defined along this line, then when we say x equals 0 minus, then we are talking about x values just before the 0. Right, so just before the 0, we are in phase 1, and here the concentration is this value, Ca1, right? And then just to the right of that, we can say x equals 0 plus, right? So that's how we denote that we are in the one phase and not the other phase. We say 0 minus and 0 plus. Then we know in which phase we are looking, right? If we've defined which direction x is and which phase is sitting on which side, then we can figure out what that means. So we are saying that at the interface, there is some equilibrium relationship between the concentrations in the two phases, right? And that's not a trivial statement, because why do we say it's at equilibrium? What if we had just some random value of concentration? What if this value was the same as the bulk value? Why are we saying it has to be the equilibrium value? So the reason we say that is that because it's an interface, there's no volume in which component A can accumulate. So there's no buffer space, right? There's no space for A to hide. So if A is going to transfer, it's going to just pop right out into this other phase here. In other words, the transfer of A at this point is so fast, right, between the two phases, it's going to reach equilibrium. There's no space for anything else to happen than for the two phases to equilibrate. So there must be the equilibrium relationship between A and B at this point, right? And then because the equilibrium value is typically not the same as the bulk value, then in that phase, there will be a shift, there'll be some transition between the equilibrium interface value and the bulk value in the fluid, right? So like we said, on this gas side, it might well be that component A is that this gas is drier than the saturation value. So here we can think of this equilibrium value as the saturation value, because A is equilibrated, A in the gas is equilibrated with A in the liquid. So A right here is going to be the saturation value, and then the bulk gas might not be at that saturation, right? So there are all these different concentrations to think about. So at the interface, we look at the saturation values, we look at the equilibrium, and we are saying it must be at equilibrium because it's such a zero volume space that there's no time for anything other than equilibrium, right? And then because the saturation value is not the same as the bulk value, then it will go through some transition. And in film theory, what we try to do is simplify this picture. So we say, yes, it's true, you will have some interface value here and you'll have some bulk value there. And what's going to happen is, yes, there is some transition between the two. However, this space is so small that we really should be treating this in a much simpler way, right? So even if the droplet is 2 millimeters in size, still this space of transition is likely to be on the order of angstroms, right? So if you go back to our droplet, maybe let's redraw it. So we've got our droplet here, 2 millimeters. But what we are talking about is the goings on right here. And so the interface that we are talking about, the transition that we are talking about, is happening in a very small space right there. Yeah, it doesn't really help to just draw it small. You can, right? So all right. Well, So this space is so small, it's not really worth going and deriving equations and deriving the whole curve here. We would like to get away with a much simpler representation. We would like to say, well, yeah, it's fine, there's some difference in concentration here, but let's just go and draw a straight line through this and connect the saturation value with the bulk value in that liquid. And let's do the same on the gas side also. We can also just draw a straight line here. Now, there's one problem with that is, you see, this curve, it never really reaches the bulk value, right? Because it's a continuous curve and it might be exponential. You see, this curve, the limit of this curve is the bulk value. But in principle, it takes an infinite distance to get to that bulk value. So in terms of an elegant representation, we actually don't have one. We actually take quite an engineering approach to this. And what we do here is just define a cutoff point. So we define the film to end at a value that is 99% of this bulk value. So if the concentration in the liquid is 1,000 kilograms per cubic meter, then we will define the cutoff point for our film. We'll say all our transition is concentrated in 990. It's concentrated where the concentration reaches 990. So we look along this curve. If we find 990 is at this region, then we define that as the cutoff, and we say, right, my film is sitting here. So our film is there now. That means all the action happens here. All this transition happens here. And then we simplify this picture and we draw a straight line from here to there, and then we draw another straight line from there to there. And you can see that in this drawing. Right, so we've defined the bulk value here. Here's 99% of that bulk value, and here's the interface value, the saturation value. So we would like to use a much simpler picture like this, because as you'll see later, this really will simplify our entire development. Okay, now the question becomes, how do you do this? How do you create a nice straight line here? And you do that by asking first, well, if you didn't do that, what would you have to do? And we know that from the theory we've been working through over the past weeks, we should be starting with something like this. So we should be saying there's a molar flux of component A, and that molar flux is purely due to diffusion. Right, so here we are just talking about a gas sitting quietly on the outside of some liquid, also sitting quietly. So when I say sitting quietly, I mean they are not flowing or anything like that. So it's purely by diffusion that component A is transferring across this interface. So if it's purely diffusion, then we can say the molar flux of A is equal to the diffusivity times the gradient. And so we are talking about in the liquid phase. So to the right here, that means 0 plus. So we want to know the gradient of A, of the concentration of A with respect to the distance in there. And of course, in principle, this gradient is not constant, right? If you look at this picture, the gradient, if you look here, that's the gradient. Then if you look here, that's the gradient, and so on. So your gradient is varying here, but we are saying now, in terms of a film, we are going to simplify this and say, well, look, there does exist some average gradient in this whole space. So we don't know what it is yet, but we are just defining there to be some average gradient. So if we have some average gradient, then we can get some kind of average molar flux. Furthermore, we don't even like working with gradients. So we don't even want a form like this. We would rather just have some nice, easy algebraic form. So I know it's called film theory as if it's really something significant, but actually it starts out as nothing but a simple engineering simplification. right? It does have profound implications. We find that we can do many, many things once we make the simplification, but where it starts out, it's nothing but a simplification like this. So we are saying we don't like to deal with this. We don't want this complexity of a varying gradient and all that. We would rather deal with something like this. And this is a typical approach. You'll find it again and again. If you find some theory you don't like, you say, well, I don't like this. Let me just propose a different theory, and let's see how the two relate. Right, so in terms of how they relate, let's think about what's going on here. So number one, this form that we are proposing, so there's some unknown constant, some Kc. So we are saying here, we know that there are two concentrations to worry about, right? There's the interface concentration and there's the bulk concentration. And we know we want to get the molar flux, right? So we would like to just multiply the concentration difference between these two by something and then get the molar flux. We want to know the flux that's transferring in across this liquid. So those are the two things we want. And so let's just bash in a constant and call it the mass transfer coefficient, right? And if we think about what these two things are, right, this is the flux due to concentration differences, and this is the concentration difference itself, then this is nothing but the constant that relates those two things together, right? So that's your mass transfer coefficient. We'll call it the mass transfer coefficient. And then what we'll say is, well, what we actually have is this, right? If we were to do this more rigorously, then we have to think about gradients and so on. So now what we can say is, well, let's think about this form a bit more and say, well, we believe that there exists, that this gradient in reality, although it's varying, let's just say there exists some average gradient. In that case, we can say that if we could just take the endpoints, right? If we take the concentration here and the concentration there, and then subtract those two and divide it by the thickness here, right? Remember, we figured out where 99% is, so that defines for us a stopping point, and then we can say that makes our film this thick. So we just divide by that thickness. So we take the concentration difference up here, and then we divide it by the thickness. So we call the thickness of that film delta, right? That's a lowercase delta. And this is then our approximation to the more rigorously defined diffusion flux, right? So those are equal. And then if we go back here and say, well, these are the same fluxes, then you can substitute this flux with our definition, right? This is a definition. We said, we wish we could write something nice and simple like this. So now we've substituted our definition, and this form is a bit closer to the reality. It's still an approximation, but we have to make that approximation. We have to do something to avoid the curve here, so we just make it a straight line. So that's what we have. And now if you compare these two, of course we are using the same concentration difference here. So we can just cancel those concentration differences, and then we have this. So we are left with the relationship between our made-up constant, the mass transfer coefficient, and the diffusivity, right? This is more rigorously defined. We've defined the diffusivity in terms of Newton's law and all of those good things. So this is a more physically defined, more justified constant. Well, we've now related our made-up constant with this diffusivity, and there's this unpleasant delta, right? This is, you could say, where all the unpleasantness is hiding, because now that means we need to know how thick a film is. And if you think about it, you know, that droplet of water, we are saying there's a little film in that droplet. It's not even the thickness of that droplet, it's a little film in that droplet. And we are saying we need to know that if we want to start with diffusivity and convert that to a mass transfer coefficient. Well, we did, if you look at tutorials 1 and 2, we did show methods for deriving the flux. So we started out with our general flux balance, and then using the flux balance, and depending on what the components were doing. So if you have component A diffusing through stagnant B, or if 1 of A goes this way and 3 of B goes that way, right? I hope you remember that whole thing. So whatever's going on, well, in this case, if it's A going through stagnant B, then you get this form. If it's something else, then you get a different form. So anyway, you derive your expression. You use your flux balance to derive the flux relationship with the mole fractions and the distance. And now you can use this equation, right, to work out where you have 99%. So we know we've got an interface value and we've got 99% of a bulk value, right? So you take your bulk value, take 99% of that, and you just fix that as being that number. You stick your interface value in here, and then you can calculate this delta x. Right, remember delta x, x is the distance, sorry, that's xa, yeah, I've switched mole fraction for x. I didn't want to confuse it with this distance x here. So this distance x minus x naught, that's of course going to be our film thickness, right? If we are looking for the position where y becomes 99% of the bulk value, then that's clearly the film thickness. So that's what we are solving for. That's how we are trying to get our delta, right? X minus x naught is the delta we are looking for. Everything else is defined, right? Ya and ya naught, right? The interface, mole fraction, and 99% of the bulk value, those are all defined. Total concentration and diffusivity, we assume we know. And then the molar flux, we do need to have the molar flux. And if you look in that, for example, tutorial 1 and tutorial 2, we had defined some mole fractions at some spatial positions. So because we knew a mole fraction at a spatial position, we could estimate a flux. And then we said the flux is constant across the space. So you use data like that, you work out the flux, and then you assume that flux is constant. So Na is known as well. So then everything is known except for x minus x naught, which is what we are solving for. So that's how you work out the delta. Right? So that gives you a delta here, and then you've got the diffusivity, and now you can get the mass transfer coefficient. Right, now what I've just described is in principle what you should do, right? It gives you the rigorous way, and obviously I'm showing you the rigorous way to do this because we are talking about this in terms of understanding it, right? In practice, what often happens is that Kc is estimated in various other ways. So you'll find later in your solid fluid courses and distillation and so on, you find that the mass transfer coefficient is an important number which relates other things going on. So it relates to the rate at which components are being transferred from one phase to the other. That's why we are interested in it, actually. But because it does that, then it has other relationships. So you can sometimes measure it a little more directly. I would say this approach is something that is more for understanding. In practice, we don't really work out mass transfer coefficients this way, but this is what it means. In my own research group, we did actually calculate it this way, and that worked out quite nicely. So you can do it this way, just that in practice, we don't really measure it that way. So anyway, we can get a mass transfer coefficient, and then what you can also do is say, well, what I'm actually interested in is not so much just what's going on here. It might be that I want to relate the concentration, the concentration difference going on here. I want to use that to get the mass transfer, the mass transfer rate. So what we can do then is relate it through the equilibrium constant. So if you look further up in these notes, you'll see that we've defined the equilibrium constant. So the equilibrium constant multiplied by that, that helps you relate your gas phase side to your liquid phase changes. Okay, so that's film theory. That's or rather, that's the idea behind film theory. and obviously we'll look at some examples, and we'll estimate the mass transfer coefficients and so on. So with that, I hope to say we have rounded out our boundary conditions. We did actually use this in the last tutorial. So this is where it all comes from. So when we define that thickness and so on, that's the theory behind it. So we want to, so just to place where this fits in, this is a critical area for defining boundary conditions. So quite often your film theory is used to define your boundary conditions, and as we said before, it shows up in many of the other design equations for distillation columns and so on. So what we want to do now is say that, well, we've completed our boundary conditions. So we've done modeling case studies in the last few weeks. So we had taken these specific situations. So for example, we looked at problems where we had, let's look at one of the cases. So in this case, for example, we had your component A that was flowing in a stream, and then component A, it was being absorbed on the walls, and there was also diffusion and all of that. So we took a text description. We started out with some text explanation of a situation, and then we went ahead and we defined the various aspects. We defined our fluxes, so we figured out what the flux was, and then we multiplied that by the right area, and we said you have to be very careful with identifying the area that's normal to the flux. And then we also figured out how to work out the number of moles in the space. We had to figure out how to count the volume, so we multiply the volume by the concentration, and so we eventually derived the equation. Now it's important to be able to do that. However, what we should be experiencing is a kind of fear here, in that it seems quite tedious that we have to do all of this every time we want to derive a balance, right? Because if you look at this description, right, and we did that last week. We said we have this flow in this pipeline, it's turbulent, and then we went ahead and derived the equations. Then we just switched turbulent to laminar, and just that small switch, turbulent to laminar, meant a whole other dimension had to be added, and it became a much more complex model. And so we are experiencing some apprehension here that this description is going to change the entirety of the model. And the reason that that's a concern to us is that what if the requirements of our design change quite quickly? And does it mean then that all our theoretical development is so dependent on a specific case? So if the case changes slightly, does that mean all our theory is out the window and we have to start from scratch? And it could be as simple as on one day we were using a cylindrical tube, like is described here, and then the next day we decided to change it to a square tube. And in terms of engineering, that's almost a trivial change. Well, it's not a trivial change, but it's not considered a change that means you have to go and redo your entire design, right? It's a fairly small change. But in terms of the theory, it means now we are dealing with a completely new geometry, and we have to start from scratch and all of that. And we don't want to do that. We suspect that because it's roughly the same stuff going on, that there must be a simpler way to deal with this. We don't want to go and re-derive everything from scratch. And that brings us to the conservation equations. So this is an attempt to generalize these approaches of developing models and so on. And of course, in this playlist, there is a detailed video on the set of notes. And in fact, what I tried to do in that video is show that our development proceeds directly from the fundamental theorem of calculus, right? Your fundamental theorem of calculus, that if you integrate the derivative, then you get the same as the difference of the function at two positions. So your basic fundamental theorem of calculus we show through derivation. It's not like we bring in any new information. We show how that becomes the divergence theorem. So the divergence theorem, according to me at least, is nothing but a higher dimensional version of the fundamental theorem of calculus, right? And in fact, just look at it this way. This is saying that if you integrate across the space, right? So function y lives in the space x. So if you add up all the changes of y across the entire space, then the result you will get of all those changes, of adding up all those changes, right? We view integration as adding up things, and here it's a derivative. So we are adding up over a derivative across a whole space. So the result of all the changes going on inside the space is simply equal to the changes that we can observe on the boundary. So in other words, we could go inside the space and add up all the little changes going on in there, or we could stand outside on the boundary and say, well, if I just look at what's coming in and what's going out, I can just see what overall what's going on in the space. And that's all that the fundamental theorem of calculus tells you. So a little bit from a chemical engineering perspective, you can understand the fundamental theorem of calculus, and it's the same as the divergence theorem, right? The divergence of a function, this you can think of as the gradients of a function. So, and here we are adding up all the gradients of the function. We are adding up all the changes of this vector field, and we get the same result if instead of working through the whole volume of the space, we just dance along on the surface. If we integrate along the area of that volume, then and we add up the changes that we see there, then we'll get the same result. So instead of having to grind our way through the entire volume and look at every single thing going on inside, we can just look on the surface and get the same result. So this result, the symbols might be new, but intuitively it's exactly what we've been saying, right? Rate of change of something is equal to the changes on the ends. So in minus out equals rate of change inside the space, right? And that's why in this entire development there's nothing really new. That's why this works, right? Because that's all it's saying. And I know it's quite symbolic and all of that, but that's all these equations are saying. So work through it and you'll see that we eventually come to a form that looks like this. And what's presented here is the Cartesian kind of rectangular coordinates, so x, y, z, not r, z, theta, not r, theta 1, theta 2. So not cylindrical, not spherical. Instead, we are looking at rectangular coordinates. So it's all nice and Cartesian. So it's pretty easy to follow, I think. And what you'll find is you get a form that looks like this. And, well, not like that. Sorry. That looks like... this. So this is the equation we get eventually. Now, what we do in this equation is we define a nabla operator. So the nabla operator here, the nabla operator is the derivative with respect to each spatial variable of some function f. So function f is living in in three dimensions. So for example, if f is simply the concentration, you can think of the concentration as being dependent on three spatial variables. So for example, imagine a box, and you can pick any position in that box, and you reference the position using x, y, z. So you can say this position is so far from the bottom, and so far from the left, and so far from the front. So you can define x, y, z, and so concentration is a function of x, y, z. And then we can look at how is that concentration varying in the x direction, in the y direction, and the z direction. So that is what this nabla means, right? It's we think of this as a derivative, but it's a higher order derivative. It's just the gradient of a field, right? Concentration is a field of values, right? You've got different values at different XYZ positions. So it's a field of values, maybe a volume of values, and you can define the gradient at any point. This is a nice convenient way of representing the gradient of a field, right? The nabla operator. So in terms of XYZ, we define nabla f in this way, and we then we can somewhat generalize our expression to this form here. So you get a form like this, and this is written in all three dimensions. So in this equation, we have not attempted to reduce the number of dimensions, right? If you look at the last couple of sessions, we were always asking, okay, is it symmetrical in this dimension? If it is symmetrical, then we can say that we can eliminate the one side of it, and then if there's no gradient in a certain dimension, we just got rid of that whole dimension. So here we are not doing that. We are not trying to get rid of any dimension. We are saying let's accept that there might be changes in all three directions, and let's just hide all of that behind these nablas. So now we've found if we do this in XYZ and we represent the nablas, then you get the equation like this. So you can follow the developments here and just be sure that you are confident this is correct. And you'll find there that we have the velocity. So you've got u times dc dz, and then you've got diffusivity d2c dz squared, for example. And I'm just looking here at what we did last week. So some of the examples we worked through, let's see that we'll see that we have a similar kind of form. Sorry, I should have opened this earlier. Okay, so here we have one. I'm looking for one with flow. So there's flow in a pipeline. So remember, we estimated the volume, and and then we estimated the flow parts and the diffusion parts, and we derived. Did we not finish this? So here we did. We did finish this. So here's what we had eventually. So you can see we have dc dt is ddz of uca, and if we look here, so we've got, think of this as ddz of u, and there's ca there. So there's that term, and then we've got ddz of diffusivity ddz ca. So that's d2 dz squared. So that's right. Nabla squared is basically the second derivative. So we've got the second derivative there and diffusivity there, and that's it. What we had here was there was a source term. So we had contribution from the walls or something like that. I can't exactly remember. I think there was reaction on the wall or absorption onto the wall, something like that. Right, so you can see it's fitting the pattern for that example. And then those three examples that are outlined as case studies, those are all carefully chosen because they represent the same types of things. So if you work through all those, you'll see they all tend to fit this general equation. And so that's starting to imply to us that this equation is nice and general, that instead of starting from each specific situation and trying to figure out all those little contributions and deriving the equation from scratch, instead we could start from this equation and then look at how we can derive the specific form. So this is an abstraction. This is a generalized version of our mass balance. It applies in all dimensions, and we hope that we can simplify this down. And then you can say, yeah, well, that's all well and good, but that applies in your rectangular coordinates. But you see, the beauty of the nabla operator is that it is defined in all geometry types. So for Cartesian coordinates, nabla looks like this, and nabla squared looks like that. If you go to cylindrical coordinates, right, r, theta, z, instead you'll get nabla looking like this. So you've got this weird extra term here, the 1 over r. And if you, again, look at the last couple of weeks, we spent some time talking about why you can't divide out the r, because the r at r and r at r plus delta delta r, it can't cancel and so on. So be sure you understand why that extra 1 over r is there. But basically we showed we had exactly that form. And then for the second derivative, it looks like that. So you get 1 over r, and then the r has to survive in here, and then 1 over r squared if you have a gradient in theta, and so on. So we did do this in cylindrical coordinates, and then for spherical coordinates as well. You'll find nabla it has that, and then you've got the angle ones here, and then you've got all these terms here as well. So you see this equation, even though we derived specific forms of it, there does exist a generalized view of this material balance, and we can then start thinking about this in terms of concept, right? We can think of this, our convection term. How much is convection playing a role? We can think of the diffusion flux term, right? And now we are not stuck to, in this specific geometry, this is how we count this dimension and so on. So that's the beauty of these equations. You can now, you can, how can I say, isolate the complexity of the geometry into these gradients here. The downside, of course, is that you are dealing with a more abstract form, and to actually solve your equations, you are going to have to seek the specific form. So for your situation, you'll have to expand this out and then think about which dimensions matter to you. So for example, when we were talking about the earlier case studies, cylindrical flow, a stream flowing through a cylindrical tube, we said that if it's turbulent, then flux in the axial direction doesn't matter. So that means your DDR doesn't matter. We said the flux in the Z direction does matter, so we keep the DDZ. And then we said also, I remember saying this specifically, the angle does not matter, because nothing in this question says that there's a particular angle that's going to influence anything. So it looks like the only variable that matters is the Z. The gradients in R and theta do not matter. So you look at this and then you say, well, I do take this specific form. So I'm working in cylindrical coordinates. Therefore, these are my nablas. However, I know that only DDZ matters, right? This is for the turbulent flow case. So we know we have to keep these. DD theta does not matter, DDR does not matter. So we can just knock out these other two terms. And so we get the specific form for nabla F and nabla squared F. And so that's what we do for turbulence. In the case of laminar flow, we know we cannot get rid of DDR anymore. So we have to keep this, this term. And if you look in our derivation, yes, when we did turbulence, then we only had terms that looked like these. And then when we did laminar flow, then we had these DDR terms. We did not have DD theta, right? But you know, if for example the problem suddenly says gravity plays a role, then it means we are no longer symmetrical around in a circular way. We are no longer radially symmetrical. So the angle does matter. If, for example, gravity plays a role, then all we have to do is retain these two terms. Right, so cylindrical coordinates, spherical coordinates we have dealt with. Typically, the angles don't matter, so we just concern ourselves with the radial components. But again, if there's some kind of shape factor coming into play or gravity or something like that, then yes, we would retain the angular parts. So I'm saying all this because this is how we could solve the problems. So instead of starting from scratch and deriving forward in each little term, we just say, look, my equation is like this. Then I just look up my system. Is it cylindrical, spherical? What kind of system is it? Okay, then I just use the right nabla for that geometry. And then what dimensions matter? Okay, Z matters, R matters, theta doesn't matter, and then and so you can derive the equation directly like that. Okay, so that's the beauty of this generalized form. Now we've talked about two levels of generalization. All right, we've talked about the geometry, and we said also that the type of equation also can be generalized. So we've so far been focusing on the mass balance, but what about energy and momentum? And if you recall what you were doing with Prof. Govender in the first part of the course, you found that you had a momentum balance that looked like this. So density times a rate of change of velocity. And you also had a convective flow term. So this was basically momentum. So your rate of change, your momentum was changing due to convection, and you had viscous drag, right? So because the neighboring fluid is dragging on the element that you are balancing on, you have to include a viscous drag, and then there might be some source term. Now, if you look at the form of this equation, you've got u nabla u, and then you've got nabla squared u. So you've got a constant here, and then nabla squared u. Now compare that with what we have here. You've got u nabla c, and you've got d nabla squared c. So it looks like there's always a convection term, and there's always a second order kind of a drag term. Right, so this we think of as viscous drag. The fluid is dragging on the other fluid around it. You can also think of this as a kind of drag. So because your neighboring fluid has a different concentration, it's dragging molecules away from where you are because of that driving force. So you have a kind of movement term and a kind of drag term. And you are seeing this pattern repeat again and again, right? So you've seen it here in concentration. You will also find it in the energy balance. So your rate of change of energy is due to, right, the things that tend to change the amount of energy is due to the flow of energy. So simply because a fluid is in motion, energy is being transferred through the space. And then energy, the thermal energy also conducts around. So due to conductivity, your temperature. So if, for example, you have a copper plate and you apply heating on one edge of the plate, then that temperature will rise slowly across the rest of the plate. So conductivity, right? Your again, the drag of things. Your molecules on the hot side are dragging the other molecules into a state of agitation. So you've got a second order nabla squared there. So you see they all fit the same pattern. And in chemical engineering, this is why we have a thing like analogies among the types of balances. There's something I also noticed. This actually comes from some research we did in electrical resistance tomography, where we use electrical imaging or electrical pulses to form a 3D picture of what's happening in a space. Well, anyway, it doesn't matter, but this is just a quick note that I've also noticed this pattern in electrical engineering, right? If you talk about your potential energy, there's a convective part. So because you have a current flow, right? That's basically like us in chemical engineering, we have a convective part. So this is basically electrical convection, right? Your current is flowing about. So you've got convection, and then you've got a kind of drag part. So because of potential field differences, then you tend to get the electrostatic flux, and so in Poisson's equation you can show that you get basically the same analog to our three main ones in chemical engineering. So it seems like nature likes this pattern. It's not actually that nature likes this pattern, it's that among all the transfers that happen, we can count them as the transfers due to things moving about, and the transfers due to the microscopic entities influencing each other. So the microscopic entities drag each other around. There's an attraction among those entities, and then the bulk body of the entities are also moving about. So this equation is kind of my proposal of a generalization of the whole of engineering, right? We are saying that if you are trying to write a balance on any quantity, so phi is an abstraction of the quantity. It can be CTU for material, energy, and momentum. It can even be E for the Poisson's equation. So your quantity of interest and the rate of change of that quantity is dependent on the movement of your fluid, and is dependent on the attraction of the entities within the fluid, and then you may also have a source term. So that's a complete generalization for all our equations, and it's also generalized in terms of geometry. So a question that I like to pose is, I'll describe some situation, and then I'll provide this equation as your your equation page. So there was this thing, formula sheets. So my formula sheet has one equation, and you basically just have to customize this equation. Well, maybe my formula sheet should also have these different views of nabla. So you customize your equation, you choose the variable that you are pursuing, then you go ahead and customize it for geometry. You simplify down that geometry, so you cut out the terms you don't need, and then that gives you the equation. And then you use the boundary conditions to specify the edges, to specify what's happening on the edges of the space, and then that's all you need. You then have a closed system of equations which can be solved to give us our final solution. So you can work through the same problems that were defined in the earlier tutorials, but now instead of starting from scratch and deriving the flux and looking at the areas and all of that, instead you start with the generalized equation. This should be an alpha, not a C, by the way. So you start with the generalized equation, and then you just take the situation here that's described in the text, and you customize it until you have the equation. And then hopefully you've done it already, but then you should also do the specific form. So this is talking about starting from the high level and moving down. Then start from the opposite direction. Look at our case studies. I think that was in notes 3. So in the third set of notes, we show various case studies, and we build up the equations by working through each of the terms. So do it that way as well. Do it both ways and see that you get the same result. Okay, and then you create the boundary conditions. So that's just and by the way, in the appendix here, I'm also showing a kind of simplified view. So if your brain is getting rotten from all these from such a high level of abstraction, then I've also provided a kind of shorter, just specifically if we want to know about the mass balance, then you can follow this one. So this is a shorter development. It might be a nice one to start with and then look at the abstraction. Okay, so that's our generalized view of all of engineering. So we've got our conservation equations now. We can do anything in all of engineering, right? Let's now think about solving these equations. So it's not enough to just have these generalized equations. So even with the boundary conditions, we still have to solve the equations by the end of the day. Now, you are, especially in your third year, going to meet all kinds of methods for solving differential equations. And I'll be meeting you for parts along the way there. But we're just going to have a quick look at some of the solutions that you can see. So I just want to get us to looking at a solution, the types of things we can do. So you have your generalized balance, and you go and figure out your specific equations for your situation. And what you do next is create approximations to that. So you create your finite difference form. So you say all your gradients can be estimated as differences between values of a function. So for example, dc dt at some position xj at some instant in time ti. So you can say the gradient or the rate of change of c at that position at that instant can be approximated as the difference of c at the I plus 1 position and the and c at I, and then at different and then across the time of interest. So you can numerically approximate a derivative, and so everything is based on that, right? Once you can approximate a derivative reliably, then you actually have everything you need to solve these equations. Because if you go to, and by the way, for second order, you can do a similar thing. So it's all in the set of notes 07. So you can work through that more carefully. But just sticking with it at a high level, you can translate any equation into these finite difference forms here. So what I mean is, your equations can be translated to get rid of all the derivatives, and now you have a system of algebraic equations that you can solve, right? So I'm just looking for a case where that's shown. Okay, unfortunately it's not really shown here, but read about the method of lines. That's basically how you can solve PDEs. And so you can solve these equations, and the problem is worked through here. And I just want to talk about the solution for a bit. So this is a case where we have I think this is a pipeline example, and you've got 2 dimensions. So you've got the distance down the pipe here, x position, and then you've got the progression of time. So we're looking from time 0, and time is passing in this direction. So at t equals 0, we can think about all the x positions here. So if it's a pipeline, and let's say it's a 5-meter pipe, so here's position 0, here's position 5, and so we are saying that in this pipeline we initially have a 0 concentration of, let's say it's component A. So we are talking about component A that's just starting to enter a pipeline. And now because A is just entering the pipeline, one of the boundary conditions says that the concentration of A just at x equals 0, just at the entry point, the concentration of A is not 0, but just to the right, it's all 0. So deeper into the pipeline, A is 0. And then if some time passes, right, remember we are still talking about 0. So this is the line. So at 0, this is the line we are talking about. Now, if we think 5 seconds, let's say 5 seconds later, what's happened? So 5 seconds later, some of A has penetrated deeper into the pipe, So you've got A that's now not 0 at small values of x. And if you follow this line here, right, you can see this curve. If you follow this curve, you can see A is now not 0 just inside, but it quickly goes down to 0. And then if you consider an even later time, so let's say we are looking at time 100, then we are looking a bit further along here, and now you can see A has further penetrated into the pipe. You do get to a 0 here, and then as you consider greater times, your curve is settling out here. So I believe here component A was reacting on the walls or something like that. So that's why it doesn't get up to 100% there. It eventually settles down to this. So basically we are saying after a couple of hours, your concentration of component A, it's high at the inlet point, and then it has this kind of steady profile to it across the pipeline due to consumption, because you are supplying A into the pipe, but you're also reacting A through the pipe. So it eventually settles down to some steady state like that. So you see, even though we've been deriving these equations in the abstract, we applied the boundary conditions, still you are able to create a numerical solution to this, and that's shown now here. So if you follow this, and I think I did try to put enough detail in here that you could actually do this. So this is all doable, right? And this is written in Python. So you can create your discrete forms of these equations, and I think I do use a library. I use the ODE integrator here. But basically you can solve problems of this type, and you can get solutions, and then you can design pipelines, and you can predict what's going to happen inside the space. Okay, that's basically it. I just want to check whether there are any questions that were sent by email so long. Okay, so that's pretty much it. That's what I wanted to cover today, and see you next time.